Let's try another recurrence equation. Let's say t of n is 3 times t of n by 3 plus n squared. So instead of c times n, we have n squared. That's the difference between this recurrence equation and the previous one that we just saw. So we are again going to use the recursion tree method to solve this equation. We start from a single node t of n, and then we expand this node by substituting the terms on the right hand side. 3 times t of n by 3 plus n square. We make n square the root, and we make t of n by 3 as the child. There are 3 of these terms because there are 3 subproblems of size n by 3. So after one round of application of or opening up of the recurrence, we get this. After another round where we substitute t of n by 3 at the right hand side of the recurrence equation. So t of n by 3 is 3 times t of n by 9 plus n by 3 squared. So we have replaced n by n by 3 everywhere. And so we get t of n by 3 is 3 times t of n by 3 divided by 3, which is n by 9, plus n by 3, the whole thing squared. So we can expand the tree up to one more level where we will replace t of n by 3 by n by 3 squared, and each of these nodes will have 3 children, t of n by 9. So there will be 3 children here and 3 children here. Again, all the nodes at a particular level have the same value or cost on them. T of n by 9 is going to be 3 times t of n by 27 plus n by 9 squared. So we can go on expanding this recursion tree until we again hit the bottom when we reduce the size of our subproblems to 1. So the snapshot of the tree at the end is going to look like this. We'll have n square at the top, n by 3 squared, n by 3 squared, n by 3 squared. This will have 3 children, n by 9 squared, n by 9 squared, n by 9 squared. Right, t of n by 9 is 3 times t of n by 27 plus n by 9 squared. And then at the next level we'll have n by 27 squared and so on. So at the very last level we will have t of 1. So if we define the topmost level as level 0, the next level is level 1, next one is level 2, level 3, and so on. At level I, we are going to have nodes with the value or cost n by 3 to the power I square. When I is equal to 0, we have 3 to the power 0, which is 1. We just have n squared. When I is 1, we have n by 3 whole thing squared. When I is equal to 2, we have n by 3 square, or n by 9 whole thing squared. When I is equal to 3, we have n by 27 squared, and so on. And the number of nodes at each level will be 1, 3, 3 squared, 3 cubed, and so on. Basically, our subproblem, the number of subproblems we have are 3. So whenever we split a problem into subproblems, we are creating 3 additional nodes at the next level. So the number of nodes goes on increasing by a factor of 3 at every level. At level I, we'll have 3 to the power I nodes. At the very final level, which we'll call as level h for the height of the tree, we'll have 3 to the power h nodes, and our problem size would have reduced to 1. So again, if we want to calculate the height of the tree in terms of in terms of n, we can do it by equating n by 3 to the power h, which is the size of the subproblems at level h, to be equal to 1. And that's where we stop. So we haven't expanded out these t of 1s because these are the base cases for our recurrence equation. We can solve these subproblems directly. So as in the previous problem, n by 3 to the power h will be 1 and h will be log of n base 3. Okay, so how do we calculate t of n? We again will take the level sums. We'll sum the costs at each level in the tree and then add those level sums to get the overall value for t of n. The level sum for level 0 is just n square. There is a single node with the cost n square. At level 1, we have 3 nodes, each with a cost n by 3 squared. And so our our level sum for level 1 is n squared by 3. At level 2, we have 3 squared nodes, each with cost n by 9 squared. And so we'll have a cost of n squared divided by 9. At level 3, we will have 3 cube nodes, each with a cost of n by 27 squared, and this will be n squared by 27. At level I, we will have 3 to the power I nodes, each with a cost n by 3 to the power I squared, and that will become n squared divided by 3 to the power I. At the penultimate level, we will have 3 to the power h minus 1 nodes, where each node has a cost of n by 3 to the power h minus 1 squared, and so that will be n squared divided by 3 to the power h minus 1. And at the very last level, we'll have 3 to the power h nodes, each with a cost of t of 1. So we can write t of n as the sum of all these level sums. So if I state the last term separately, 3 to the power h multiplied by t of 1 plus a series where we are adding the values of these level sums. So we are adding terms of the form n square by 3 to the power I, where I varies from 0 to h minus 1. Right, when I is equal to 0, we have the cost of n squared, which is the cost for the topmost level. And when I is equal to h minus 1, we have a cost of n squared divided by 3 to the power h minus 1, which is the cost for the penultimate level. So this is the expression for t of n. Let me write that down separately so that we can simplify it. T of n is 3 to the power h multiplied by t of 1 plus summation of I varying from 0 to h minus 1 n squared divided by 3 to the power I. Now again we have determined h to be log of n base 3, and so we can simplify the first term to 3 to the power log of n base 3 times t of 1, and this is nothing but n. From the second term we can extract out n squared, and we get this series I equal to 0 to h minus 1, 1 upon 3 to the power I. Now this series is a geometric series. A geometric sequence is a sequence of terms of the form a, ar squared, ar cubed, and so on, where we have a first term and then each successive term is obtained by multiplying the previous term with some number which we call as the common ratio. In this case it's denoted by the letter r. So we multiply a by r, we get ar. We multiply ar by r, we get ar squared. We multiply ar squared by r, we get ar cubed. Looking at it another way, if you take the ratio of the nth term with the n minus 1th term, we will always get a ratio of r, and so we call r the common ratio. So ar squared by ar is r, ar cubed by ar squared is r, and so on. When we sum together, say, k terms of a geometric progression, we get a geometric series. So a plus ar squared plus ar cubed and so on, then ar to the power k minus 1. So these are k terms. This is called a geometric series. And that is what this is. So this is the series 1 plus 1 by 3 plus 1 by 3 squared plus so on till 1 by 3 to the power h minus 1. There are h terms in this series. The first term, which is a, is 1, and the common ratio is 1 by 3. So each term is obtained from the previous term by multiplying the previous term by common ratio, which is 1 by 3. How do we solve for the sum of k terms of a geometric series? Well, if we write S as the sum of the k terms, a standard way to solve for S is to multiply both sides of this equation by the common ratio, which is R. So if I multiply the left hand side by R and the right hand side by R, I'll get AR plus AR squared plus AR cubed plus so on till AR to the power K. But instead of writing those K terms directly below these K terms, we write them in a slightly staggered way. So we write the first term here, AR plus AR squared plus so on till AR to the power K minus 1 plus AR to the power K. So this is nothing but the right hand side multiplied by R throughout. By writing the right hand side in this staggered form, we can take the difference between these two equations. So if we subtract the second equation from the first, we get 1 minus R times S is equal to the first term here, A. Now when this AR is subtracted from AR, we get 0. When this AR squared is subtracted from AR squared, we get 0. So these two terms cancel out. So in effect, we have paired together most of these terms so that they all cancel out when we take a difference between the two equations here. And we'll be left with the first term of the top series and the last term of this bottom series. So we can say that S is A multiplied by 1 minus R to the power K divided by 1 minus R. Usually we write it like this when the value of the common ratio is less than 1. If the value of the common ratio is more than 1, then we usually write this as A multiplied by R to the power K minus 1 divided by R minus 1, so that both these terms are positive. If R is less than 1, then these two terms will be positive. Okay, so having derived this expression for the sum of k terms of a geometric series, we can now write an expression for this geometric series. This has h terms, and let's go to a different page. T of n is n times t of 1, right? 3 to the power log of n base 3 is simply n multiplied by t of 1 plus n squared times the sum of these h terms making up the geometric series. I'm going to call this a decreasing geometric series because the value of the common ratio is less than 1, and so the terms are decreasing as we go down the series. Or looking at the recursion tree, as we go down these levels, the values of the costs are geometrically decreasing. Okay, so the value of this series is the first term, which is A, multiplied by 1 minus the common ratio, which is 1 by 3, which is raised to the power k, which is the number of terms in the series. and the whole thing divided by 1 minus r. So this can be written as 1 by 3, the whole thing raised to the power h, because there are h terms in the series, divided by 1 minus 1 by 3. So this is 3 to the power h here is again 3 to the power log of n base 3, which is n. So we can write this 3 to the power h, we can replace this by n. So we get, so 1 minus 1 by 3 here is 2 by 3. When we take this up, we get 3 by 2 multiplied by 1 minus 1 by n. That's this series. And it's multiplied by n squared. So we get t of n as n times t of 1 plus n squared times this expression. So the first term is 3 by 2 and the second term is minus 3 by 2n. So you can see that the dominant term here is n squared, and so we can write t of n as theta of n squared. The difference between this recursion tree and the recursion tree for the previous problem was that the level sums in the previous problem were the same at each level. Right? In the previous problem we saw that the costs at each level were simply c times n throughout. And because there were log of n levels, the overall cost was Cn log n approximately, which was theta of n log n. Here, the costs are not the same across all levels. The costs are geometrically decreasing down the levels. The last term, of course, is written separately, but you can see that if the costs are geometrically decreasing down the level, the overall complexity is proportional to the cost of the first term of the geometric series. And that's an interesting point to note. If you have a geometric series where the common ratio is less than 1, that is, the terms are decreasing, then the value of the series, or the complexity of the series, the asymptotic complexity, is primarily determined by the first term of the series. So in this case, the first term was n squared, and the common ratio was 1 by 3, and this was a decreasing geometric series, and we saw that the complexity of this whole series is theta of n squared, which is basically the complexity of the first term. We are also going to see that if we had gotten an increasing geometric series, in a few videos from now we'll take an example where instead of a decreasing geometric series we get an increasing geometric series. You'll see that for an increasing geometric series, the complexity of the series is primarily determined by the complexity of the last term of the series instead of the first term. So t of n is theta of n squared, which was basically the complexity of the first term of the series. This very last term, 3 to the power h multiplied by t of 1, it had a it turned out to be a lower order term, and so we could ignore it. And so, because t of 1 is constant, the dominant term ends up being 3 by 2 n squared, and so we can write t of n as theta of n squared.